In the last video, we talked about models of quantum computation, including the Adiabatic model, which was a continuous time model of quantum computation, where we change a function we want to optimize from an easy one to a more difficult one. And if we do it slowly by some thermodynamic arguments, we can stay in the lowest energy state and maintain our place at the optimal solution. And then at the end, we're in the optimal solution. The measurement-based model of quantum computation started with a highly entangled state, and we perform individual qubit measurements adaptively in the sense that we choose which measurements we're going to perform based on the results of previous measurements. And if we do this in a clever way, then we can solve some problems that we're interested in. And then the circuit-based model, which is the one that we've looked at already by drawing these quantum circuits, and the one we'll continue to look at. I wanted to mention those other models because we can map our problems back and forth between them, and they're quite distinct, so it's quite an interesting thing to think about these other models of quantum computation, which look and feel much different even though they're equivalent. Within the circuit model, there's a more interesting sort of foliation of submodels, you might say, and those are defined by which gates we're going to use. So not all gates are created equal, so I can have large gates that act on many qubits, I can have a single qubit gates, I can have a large variety of gates, I can try to choose a small set of gates, I can choose maybe simple gates, ones that we've seen where there's in our matrices that we wrote down have lots of zeros in them or no complex numbers. So how do we choose these gates? In this video, I'm not going to tell you how to choose them, how to choose a good gate set. I'm actually going to show you which gate sets are bad and kind of build up our intuition for what a good gate set might look like. So first and foremost, we have a really kind of obvious, really bad gate set, which is the one that just contains the identity inputs. Okay, so obviously we can't choose any gate set because this one here doesn't do anything. How about building up? We've seen this Hadamard gate, and what did it do if I had a quantum computation and it started in the canonical zero state in the computational basis, and I perform a Hadamard on each of those qubits, they're going to end up in the plus state. And we know from our tensor products that this is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And that is interesting because it's a really great superposition because it contains all possible basis states. So it's like the most superposed state. And as we increase more and more qubits, we end up with a superposition over exponentially many of these vectors, these basis states, because there's an exponential number of binary strings. So when I apply a Hadamard to each qubit, I end up with a uniform superposition over all basis states, all binary strings. However, you'll notice just by the drawing that there's a clear sort of cut here where I don't actually need to describe this computation as two qubits. I can describe them as, well, two individual qubits separately. So remember when we talked about entanglement, we said that if we create entanglement, we can no longer think about two separate objects. We just have this one piece of quantum information which described both qubits simultaneously, and we couldn't specify what that was by saying what the state was for the individual qubits. But here, when there's no entanglement, I can write down classically this 2x1 vector and apply 2x2 matrices to it, and if I have n qubits, well, I can just do that n times, and that doesn't grow exponentially. So not just Hadamard gates, any single qubit gates. If that's all my gate set is restricted to, then I don't generate entanglement, and I can very easily simulate such a computation classically. We saw the gate we used to generate entanglement was CNOT. However, if you look at a it gets hard to draw these circuits, so I have a little trick up my sleeve. So we're going to go to this circuit simulator. So a drag and drop circuit simulator. Here's the web address. So you can have a look at this circuit simulator. You drag circuits down onto the gates, and what are we trying to do? We're trying to drag circuits, create CNOT circuits, so I can look at a NOT gate and I can control it on a different, control it from a different gate. I'm not doing anything clever here. All I'm doing is just kind of choosing random placements, trying to make a complicated computation out of CNOT gates. So we'll put a whole bunch of these things in a random looking pattern, and we'll see if we can generate an interesting state. Okay, so how you can see that, well, the control NOT gate only changes things if the control is in the 1 state. So if the control is in the 0 state for all of these qubits, then in fact nothing happens, and that's kind of what this is showing you. You can see that the amplitude of the all 0 state, the computational basis state, is 1, and the amplitudes of all the other ones are 0. So we need to put some 1s here. So what happens, I guess what we can do is switch all of these to 1s. So if I put a NOT in front of all of these, it's going to make them all 1s. And you can see what's happening as I do this. The amplitude 1 just shifts around, and you can do that by looking at the computation. So if we look at the computation, here I have a 1 in the control that flips this 1 to 0. So now I have 1 0 1 1 1. This one flips this 1 to 0, so now I have 1 0 0 1 1. The original one now flips this one back to 1, so I have 1 1 0 1 1, and so on. And I can just step through, changing a single qubit at a time, and I never, again, I'm not generating any superposition in this case. So this isn't even classical, doesn't even allow you to do classical computation. It's a strict subset of classical computation. So this doesn't even generate. Let's point out that the above has no entanglement, which is not good, and this one has no superposition. Okay, so the obvious next step is to use a CNOT and boost it up with some superposition. Okay, so let's go back to our circuit simulator and let's put some Hadamard gates in. We can get rid of all these NOT gates. So we start in some canonical state, and let's put some Hadamard gates in. Let's put a Hadamard on everyone. And what's happened? I mean, it's a bit difficult to see, but what's happened is that although the amplitude may end up with a negative number, there's a uniform superposition over all possible states, and what's happening is, at least in this case, I will just get a completely random outcome. if I start putting Hadamards in other places, you can see that things change. However, if I look at these values, then again, they're all the same value, except some have a minus sign in front of them, but I'm certainly missing out on a really key aspect of quantum computation, which is there's no imaginary numbers anywhere in the circuit. So such a circuit, which only ever produces these superpositions that have plus or minus 1 up to some normalization, clearly isn't going to cover all possible quantum computations I can do. So this has no complex numbers. And you can get quite sophisticated gate sets. So we can have, let's add one more that has a complex number. So Hadamard, and then the S gate, as it's called, where S is 1, 0, 0, I. So it's this phase gate that we looked at earlier, much earlier. So now I can generate complex numbers, but in fact, it's a bit more subtle to see. In fact, in a sense, you can't even see, but it's a result within the field of quantum computation that this gate set you can efficiently simulate classically as well. So it's not obvious to see, and you need a kind of more clever representation of the information, but even that's not enough to perform universal quantum computation, even though I can generate superpositions, I can generate entanglement, I can generate complex numbers. Now, in the next video, we're going to see that, interestingly, we only need to add a single gate, a single qubit gate to this gate set, and we can generate universal quantum computation.